So hello everyone. I'm Joel, and I want to talk to you about the GPU file system that I'm developing. And just before we get into the topic, let me just quickly tell you something about myself because that's related. I'm a professional game developer, mostly on the programming side, but also some tech art stuff. And as someone who likes games and who's a game developer, I like real-time rendering, and I love shaders, and I like to see the different technologies that just work with them. Um, and I miss hardware acceleration on Plan 9. So that's basically the plot line of everything. I miss hardware acceleration on Plan 9. Um, and before we go into the topic of the file system itself, we have to talk about what a GPU is. A GPU is a coprocessor similar to the FPU or any other coprocessor that you might know. But I think it's something more than just a coprocessor. It's more complex and it has its own memory, its own power management, its own cores, its own instruction set, actually different instruction sets per generation. And as that, I think it's just fine to also call it a separate computer because that's basically what it is. It's initially called the graphics processing unit, of course, because it's about graphics. First 2D, then later also 3D. But it can also do much more than just graphics. Especially in the last years, we have seen quite a few improvements about indirect rendering and mixing between compute parts and the graphics parts. So in that case, it's also possible to run compute shaders. Compute shaders are basically also shaders, but they are not inside that strict rendering pipeline. It's just about processing data, basically. And that's also called the GPU, the general purpose GPU. You will probably hear that a lot, but not in this talk. I try to keep it at a limit. The GPU is also the best example, in my opinion, for the SIMD, the single instruction multiple data, because graphics are something you can just imagine. You can see it in your brain. If you think about an image, it's thousands of pixels, sometimes even way more, but it's often the same process for each pixel. And that's basically the perfect example for SIMD. A GPU can run a program 1,000 times with different data in parallel. The bigger issue about GPUs, but we won't cover that in this talk, is that you have different generations. Each generation has a little bit of a different architecture. But these are all the technical details that are just hidden behind the API or behind the driver. So in the next slide here, let's talk about the application architecture. But first, let's talk about the application, because not all applications are the best example for GPU acceleration. An application can be anything. It can be a game. It can be a mining machine. It can be an offline renderer. Basically, everything that profits from having huge amounts of data and has to process them with the same instructions, basically. So in this image here, you can see 3 different possible architectural layouts for the applications. The most important for us are the first or the top 2 layers. It's the application and the file system. Because everything below the file system is abstracted behind the file system, obviously. So the application doesn't know about the driver, it doesn't know about the network, it doesn't know about virtual machine, it doesn't know about anything. It's just talking to the file system. And that's also the most important point here. The file system is the resource abstraction point, like usual with Plan 9 file systems, of course. And this file system interface should also remain the same across all implementations of the file system. So if you have a GPU file system for draw term, or a file system for a kernel on ARM, or a kernel on any architecture, basically, the file system interface should be the same. This also means that your application, of course, can use different GPU file systems based on what you bind there. Quite flexible. But since we're talking about the file system, it also has a big impact on performance, because our file systems are 9p file systems, and 9p could introduce a big overhead. But that's also something that we can explore in the future when we have working systems. So nothing to be worried about yet. Yeah. This slide also tells us that the scalability is in the responsibility of the application. That means that the GPU file system itself obviously can't know about the application and the use case of the application. So the application itself must scale. This can happen for games, for example, by drawing less, using culling techniques, drawing things at a smaller detail. Basically everything that we know from game dev perspective, but there are also non-game dev tasks. And those non-game dev tasks are a bigger issue because you need accuracy in the data. We're talking here about simulations or scientific tasks, statistics, whatever. But in those cases, I think that it's also fine to just get rid of the performance, basically, because slower is fine. Next, let's talk about the Vulkan, because the file system itself is very much inspired by the Vulkan API. Vulkan itself is designed by Kronos. Kronos also designed OpenGL, for example. And Vulkan is very low level, especially compared with DirectX and OpenGL. A program that's written for OpenGL can be like 100 lines, while an example in Vulkan would be like 200, 300, 400, or even 500 lines, or maybe even more. The benefit of Vulkan is that it's abstract and cross-platform. That means you have your own shader language, SpirV, that's also cross-platform. You can just copy that shader program from one platform to the other and it will work. And it's available on Windows, Linux, Android, Mac, and probably a few others. Yeah. The Vulkan itself thinks about shaders and buffers as objects, so that also transfers nicely to a file system hierarchy. And I also have a small image for you, because that's basically what the interface might look like, or the flow is. You put your shaders and your buffer into the file system. The file system uploads and downloads data from the GPU to the CPU memory. And your shaders will be compiled and uploaded to the GPU. And of course, the commands like run this shader, run that shader, that's also scheduled by the file system. And everything is, of course, executed on the GPU itself. To get a program to work on the GPU, you of course need to have the program in a language that the GPU understands, so you have to compile it. And usually you don't write the SpirV code yourself, you use a compiler to compile it from some GLSL, HLSL, any other high-level shader program. In this case, I have the GLSL example because OpenGL is the next big brother from SpirV, from Vulkan. And this GLSL program can be compiled to the SpirV program. And that SpirV program can be handed over to the driver, and the driver will compile it down to a native program for the specific architecture, for the specific GPU. It will also upload it, and then this code can be executed. So there's lots of magic that's happening in the driver. You don't have to worry about it. Even the file system itself doesn't have to worry about that. And the SpirV program itself is cross-platform. It's not machine-specific. It's you can really copy it from one system to the other, and it will work. It's more or less a description of the program. So you can also use it to cross-compile from one shader language to another. Even all the variable names and everything is still there. And that's quite incredible. Also, it's not just that you get a compiled version from GLSL to HLSL, but the HLSL program will also work. There's no restriction, no limitation. So with that compiled program and a rough information about what Vulkan is and what it does, we can talk about the file system. But at this point, I just have to give you that disclaimer. It is a work in progress on purpose. There are no guarantees that it will work. There are no guarantees that the things won't change. I expect that things will change. especially the interface itself. But anyways, I will show it to you. I had a few requirements for the file system interface, especially because, yeah, I'm working on it only in my free time, so yeah. It should be simple to understand. That's one of the most important things here. It should be easy to develop applications for it, and it should be easy enough so you can also handle it by hand. So you can type in the commands manually, you can pipe in your own shader programs and your buffer data via a shell script or anything like that. That's one of the things that I want. It should, of course, also be generic enough to be portable, because Plan 9 is portable and file systems are about resource abstraction, and that's also basically portability. That also makes it plug and playable, so you can just import a file system from any other machine in your network and you can benefit from the GPU processing power. Also great for laptops or anything like that, where you just want this as a terminal and your file server or your CPU server has the power and also the GPU. And it will be GPU first, so we will only focus on compute shaders in the beginning. Here in this image you can see the rough layout of the file system. It's supposed to be in the dev folder because it's a file system, it's a driver basically, a kernel device in most cases. And this file system has its own control file that's for the whole GPU file system basically. And then it has the descriptor table, more on that in a minute. And it has its objects as folders. So you have object 0 and object 1. The one is a buffer, the other is a shader. Both of them have their own control files, and both of them have their own data files. So you can upload your buffer data into the buffer file, and you can upload your shader program in the shader file. That could look like that. You can just pipe in, let's create a new buffer with 4 bytes length and a new shader. So that we have this, I have it commented here. You have object 0 and object 1, a buffer and a shader. And to load your data in, you can just copy the data in there. Yeah, now about the descriptor table, because that's something I have to explain. It's a technical thing. It's a lot about how Vulkan and OpenGL see the resources on the GPU. Probably also DirectX, I don't know. In this case, you can see one descriptor pool, and this one descriptor tool has 2 descriptor sets, and those the first descriptor set just has 4 bindings, and those are buffer bindings. So for a shader to access a specific buffer, you just don't tell it to access buffer 0. You tell it to access the buffer that's bound to this specific binding here. This gives you the power to switch buffers basically instantly, because you don't have to wait for the GPU to copy data around. So your shader basically points to this specific pointer, and this pointer points to the buffer. The shader is bound to the full descriptor pool. So in this case, a shader could be bound to the descriptor pool 0, and the buffer is bound to one specific binding inside a set. In this case, buffer 0, the one we have created earlier, is bound to the second, or index 1, binding of the first descriptor set. This is confusing, and you will see in a second in the program. I have an example shader program for you, just so you can understand it. This is the example shader program. It's written in GLSL, and only because SPIR-V is very long and confusing, so let's just talk about the GLSL version. This is 12 lines of code GLSL, which would be like 55 lines in SPIR-V assembly. You can basically ignore anything in this program. I will just point out those three important things here. The first important thing is the first layout line, which tells our shader that it will access binding 1 of set 0. So it's basically this slot entry here, set 0, binding 1. And it's a buffer, and it holds data. That's basically what this thing here says. There's also some matching about the STD 430 here, but in this case, let's just ignore it. And the second important thing is the layout line itself, the second layout line. And this tells us that the work group that this shader will be executed in has a size of 1000 in X direction and 1 and 1 in Y and Z direction. So it's basically one-dimensional. Out of 3 dimensions, we focus on only 1 dimension in this program. And also in the third important thing of this program, we also only focus on the X coordinate of the invocation, because each invocation of the shader has its own specific global invocation ID. And that's a variable we get from the system. And out of that ID, we use the X coordinate to access the right data inside the buffer. And then you can do something beautiful with a position. Congratulations. I glanced on the workgroup with you. So let's just take a deeper look in what a workgroup is. A workgroup is basically very, very necessary and important if you run a shader on a GPU. Because you don't just run your shader program once or twice or 100 times at times. You basically dispatch your shader to the GPU a number of times. And inside the GPU itself will dispatch a number of invocations for that shader, for each invocation, or for each dispatch. So the application tells the GPU, for example, hey, I want you to run 100 workgroups of that shader. And the shader itself says, how big is my workgroup? That's the workgroup size. So just to give you an example, you want 1000 invocations, which is quite a lot. Not in GPU terms, but for us to imagine. You have a size of 10, that's possible. But then you also have to dispatch like 100 workgroups of this shader. Or you can say, okay, my size is 100. Then you only need like the 10 invocations or the 10 workgroups. Those two examples can be a huge performance difference, but that's also something that we don't have to worry about. That's also relevant for the application developer. You have seen that the workgroup size itself is a 3D vector, and the same also applies to the number of the workgroups. So if you, as an application, say, hey, I want you to run this shader in this amount of workgroups, then this amount of workgroups is a 3D vector. In total, your shader has this, you have seen it, this global invocation ID. And the maximum number of the global invocation ID, of course, depends on the number of workgroups and the workgroup size. So your number of invocations is those both values multiplied. And with a 3D vector and large numbers like 1000, you can imagine that those numbers can be really, really high. Yeah. That's almost basically it. I still want to tell you about the implementations that I did, or that I didn't do. Yeah. At first, I started with the draft implementation. That's a fully CPU-based implementation. That was my implementation when I was also writing the paper. Its focus was on the file system, and I paused it because, yeah, I wanted to refine the interface just with an actual GPU. And that's why I started the drawtime implementation. It's using an actual GPU, using the Vulkan SDK. And I want to use it to verify and refine the file system interfaces and fix issues and also get nice images. And also then at that point, then we will also hopefully have something that just works, so we can use a GPU in Plan 9 software. And there might also be others in the future. I just recently learned that CPUs sometimes have their own SIMD functionality, which could be used. That's the SSE stuff and whatever, different versions, different architectures from different manufacturers. I don't know. There could also be some network implementation, hardware, whatever you want. And that's something for the future. Maybe someone else will do it. I probably can't. But yeah, so this is basically also my last slide because I don't have images of working GPUs. So thank you, everyone. And do you have any questions?
Hey, Joel, can you tell us more about how the GPU programs are compiled depending on the generation of our architecture? Is it something the SDK provides, or you have a separate toolkit for that? Yeah, can you a bit elaborate on that? Thank you.
Hi. As far as I know, that's basically handled inside the driver itself. So even the SDK just forwards basically part of the shader or the shader itself to the driver, and the driver will convert it to a format that can be run on the GPU. I hope that answers the question.
Yep, I see nodding.
Great.
Okay, one more question.
So how much of the complexity of the entire driver stack do you plan to expose, and what have you decided that you want to leave out on purpose?
That's a very good question. And I can only say that I don't know yet. I really hope that we can make everything available, but that's also just a question of how much time do we have, what makes sense. It's a question in like 2 or 3 years, if we even still need the graphics pipeline. Maybe we don't need that at all, because maybe everything is compute-based then. So we will see.
Great, one more question coming.
Do you have any ideas what you think the file system would look like for the graphics part of it, though, when you get to that? How to expose, like, is it going to be a frame buffer looking file, or some way of just setting up the pipeline, or what?
Especially in the beginning, I can imagine that everything will mostly be compute-based, and that the compute shaders can write into a buffer, and that buffer is basically just an image of DevDraw. That's at least something that I can imagine.
Right, looks like that's it. So thank you very much again.
Thank you.